All right, welcome to today's YouTube video, and we're going to talk about statistics and cytometry for dummies. So, if you've ever been in a webinar or YouTube and you heard about the terms like paired or unpaired analyses, multi-group, two-group, and you were confused, didn't want to ask questions, didn't want to look dumb, you're in the right place. We're going to teach you a quick, gentle introduction to how statistics and cytometry works. And just a reminder, our mission at TACO is to make high-parameter cytometry simple and routine for clinical trials. I'm Ramji Srinivasan, co-founder and CEO. So, who cares about this? Well, it's anybody who's been to a conference and heard these crazy terms like parametric models, non-parametric, and is scared, doesn't know what it means, but has a big drug trial on the line and wants that drug trial to win and succeed. So, these are the people that this webinar is designed for. And more to the point, these are immunotherapy developers analyzing a big cytometry data set who are looking for statistically significant differences between groups. The groups can be responders and non-responders, dose and, say, medium, low, high dose, or groups like time points. So all of those are different kind of groups that you can look at. So moving into types of tests. The first one is paired and unpaired, and the simplest way to think about the difference between these are paired tests compared related measurements on the same subjects, and unpaired tests compare an independent group. So let's look over here on the paired tests. You can see T cell percentage before a drug and T cell after a drug. You've got patient 1 over here, patient 2, patient 3, etc., etc. And paired tests are asking a question, within a patient, is there a statistically significant change? So within this particular patient, is there a statistically significant change? It's not asking at the group level. So it's asking at the individual level because there's a logical connection between a patient before he or she is given a drug and afterwards. The second kind of class is unpaired, which is comparing independent groups. So imagine you've got these control patients over here who could be either treated with a regular standard of care drug, and you've got patients on this which potentially have the experimental drug. So these are two logically distinct group of patients. So this isn't the same patient in each group. And you can see over here, there's an average for each group. So for example, the percent of T cells, this side is 40%, and over here it's 48.4 for the people with the experimental drug. So the question being asked here is, across these two different patient groups, is there a statistically significant change? So between the control and experimental drug. Okay. Now moving to two-group versus multi-group, which is exactly what it sounds like. So two-group, you're asking, are there exactly two groups that are statistically different? So here you can have a treated group and a control group. You can have a measure like the CD8 T cell frequency, and you want to see, are across these two groups, are they statistically different? And then multi-group, which is at least one group different from the rest for more than two groups. So for example, for 3, 4, 5, 6, 20 groups, etc. So you can have group here, which is low dose, medium dose, and high dose. So that's 3 groupings. And each of them has a measurement like NK cell frequency. And you can see this mean over here. And this multi-group test is intended to tell you, is at least one group statistically different from the rest? Importantly, it doesn't tell you exactly which one, it just tells you conceptually that at least one of them is different from the rest. Okay, so we talk about paired versus unpaired, two-group versus multi-group. Now let's go to parametric and non-parametric. So parametric, this usually assumes data is normally distributed or close to it, and non-parametric assumes nothing about the underlying data distribution. Parametric is one of the most powerful kinds of tests, but certain conditions need to be met. For example, the data can be characterized by some kind of parameters. We're not going to cover semi-parametric, but that's a combination of both of these, parametric and non-parametric, where parts of the model are based on a parameter and others are non-parametric. So you've got these 3 different groups, and we can sum them up all together, which is, you can start at the top, which is, are you comparing more than 2 groups, which in case you do multi-group statistics, or are you doing 2-group statistics? And then within those, you can do comparing results within a patient, or comparing results across patient groups. That gets us to the paired versus unpaired distinction. And then you can drill down further, which is the parameterization of the data set, which is, do you think it's normally distributed or non-normally distributed? And for each of these, there are different tests that are available, everything from paired t-tests, Wilcoxon signed rank, unpaired, Mann-Whitney U-test,
So these are the results, or excuse me, the different types of tests that one can use depending on assumptions about the underlying data and the intended use case. So let's zoom into one very important example, which is called multiple test correction. And this is if you have many tests that you're doing simultaneously. This applies to longitudinal changes in cytometry. So multiple test correction helps reduce false discoveries when you have hundreds of tests. So this risk of false discovery is higher when you're making hundreds of comparisons, and that's routine in these high-dimensional cytometry data sets where you have potentially dozens or hundreds or thousands of tests that you're doing simultaneously. The y-axis is the percent of top level. You can see the box plot over here. Looks like the second one is distinct from the rest, and an FDR that's vanishingly close, basically near zero, means that you've got a very high chance that this is a real discovery. 0.05 is the cutoff for a false discovery rate. Then you've got monocytes, day 0, day 1, day 7, day 14, and the percent to top level. And this FDR is 0.343, so well above that 0.05 cutoff, and even visually you can see this. There probably isn't going to be a big statistical difference between these. And then you've got another population like B cells, day 0, 1, 7, 14, percent to top level, also vanishingly near zero. So these are B cells, and you can see a similar dynamic play out. And on and on and on. So you can be doing this kind of tests across hundreds or potentially thousands of comparisons. And so what this is intended to answer is, for each cell type, is there a statistically significant difference in the percentage of that cell type across all time points? That is there at least one time point where the percentage of that cell type is significantly different than the average of the rest of the time points? So it doesn't tell you which one. You could probably guess from looking at this one, but it tells you that there's at least one cell type that's different from the average of the rest. So zooming in, we can see the cell types for which there is at least one time point where the percent of that cell type is significantly different than the average of the rest of the time points. So let's zoom into the CD4 T cells. You see a vanishingly small false discovery rate, and this kind of technique helps mitigate the risk of false discoveries in high-dimensional cytometry data sets.
So in sum, we've covered some very powerful tests, multi-group and two-group statistics, paired and unpaired analyses, as well as different kinds of parametric distributions. And the specific type of test you might need could depend on the particular use case of your data set. And so these are very powerful tools, and put in the hands of drug developers that can enhance the chance that you're seeing real signal in your data set and not a potentially false or misleading signal that could lead to catastrophic results later. Now, if you're interested in these kinds of tests, check them out at app.takeo.bio. We've got plenty of data sets you can play around with. You can see these statistical tests live. You can see immune changes over time. You can do immune differences. You can compare doses, responses, things of that nature. And if you're interested in more topics like this, like, share, and subscribe to our YouTube channel. So thanks for signing in.